Big old fat fecund female fish, otherwise known as a BOFF, BOFFFF. And yes, that's a real scientific term used in fisheries biology, but the science behind it fundamentally changed how researchers think about fish populations and fishery stability. For decades, fisheries science focused mostly on abundance, how many fish exist, how many are harvested, how quickly populations recover. But scientists noticed something strange. Two populations could have similar biomass on paper, yet recover very differently after environmental stress. One major factor turned out to be age structure, more specifically, large old females. Once researchers began measuring reproduction by body size and age instead of treating all mature fish equally, the differences became enormous. In Hawaii, researchers found a 27-inch bluefin trevally produced roughly 84 times more eggs than a 12-inch fish of the same species. Similar patterns have now been documented across rockfish, cod, snapper, striped bass, haddock, and lingcod. In many marine fish species, reproductive output scales disproportionately with body size, because larger females allocate substantially more energy towards gonad production. But researchers soon realized the most important difference wasn't just egg quantity, it was offspring quality. Studies on rockfish found older females produce larvae with larger lipid reserves and improved body condition at birth. Those energy reserves matter because larval fish experience extreme mortality during their first weeks of life. Currents, prey density, temperature shifts, and predation pressure can all determine whether larvae survive long enough to recruit into juvenile habitat. Larger energy reserves improve starvation resistance, swimming performance, and early survival probability. Older females also tend to spawn across longer seasonal windows. Instead of concentrating reproduction into one short period, large females may release multiple batches of eggs over weeks or months. Studies on Atlantic cod found spawning duration could range from roughly 4 to 15 weeks depending on population, age structure, and environmental conditions. That reproductive spread acts as a biological buffering system. Ocean conditions constantly fluctuate, currents shift, plankton blooms change timing, temperature regimes vary week to week. By spreading reproduction across time, older females increase the probability that at least some offspring encounter favorable conditions. A fish population dominated by younger age classes may appear healthier numerically while functioning very differently biologically than one containing older fish, because older females contribute disproportionately to recruitment stability, larval survival, and long-term reproductive resilience. In many marine fish species, the oldest and largest females become disproportionately important to the long-term stability and recovery potential of the entire population.